In section 3.2, we're going to cover some of the basic differentiation rules for rates of change. Starting with section theorem point 3.2, this says that the derivative of any constant function equals to 0. Intuitively, this makes sense because if you were to think about a constant function has no change at all between values, so its derivative or rate of change is going to be equal to 0. If we look at the following example, number 1, if we have the function y equals to 7, then its derivative would simply be equal to 0. If we have y equals k times pi squared, where k is some constant, we know that pi is a constant, therefore so is pi squared, and any constant times another constant would still produce a constant. So because we have y equals essentially just some number, its derivative is also going to be 0. S of t equals to negative 3, that's a constant, so its derivative, s prime of t, would be equal to 0. And in part D, the derivative of a constant, even if that constant is 0, will still end up being 0. One of the more important rules that we'll be using throughout the entire rest of the class is the power rule. And what the power rule tells us how to do is differentiate x to a power. So let's suppose that n is a rational known number where n is different from 0. Then to take the derivative of x to a power, we simply bring the power out in front as a multiple. So this is going to be n times x, and then you reduce that previous power by 1. So it's going to be to the x to the n minus 1. For example, if we wanted the derivative of, let's say, x to the 4th, you would simply bring the power down in front as a multiplication, multiply it by x, and then reduce the power by 1. 4 minus 1 would give us 3. So the derivative of x to the 4th is going to be equal to 4x cubed. And kind of going back to the previous section, we realized just kind of exactly how much of a huge time saver these things will be. From this point on, whenever we do derivatives in the class, we will invoke and use some of these limit theorems. We will not have to kind of plug this into that formal limit definition of the derivative. And if you can kind of think of exactly what this would look like, if you wanted to find this derivative by hand using the limit definition, that would be kind of a pretty long and involved calculation, because you'd have to take, like, for example, like an x plus delta x to the 4th power. Instead, we can simply use this brand new power rule. The derivative of x to the n is n times x to the n minus 1. In example 2, let's find the derivative of each function. Here, f prime of x, we're simply going to bring the power down. That's going to be 6. X to reduce the power by 1. 6 minus 1 is 5. So the derivative of x to the 6th is 6x to the 5th. Let's take a look at g of x. G of x is the cube root of x. We recall from pre-calculus that you can rewrite a root as a fractional exponent. This is equivalent to x to the 1/3 power. This step is a very, very important one and something we're going to see a lot this semester. And that's the idea of rewriting an expression before trying to apply a calculus rule. Oftentimes, if you can rewrite or re-express the function using the rules of algebra, or on occasion using a trig identity, we can rewrite it and put it in a form that will make the calculus applications and steps much, much easier to do. Now that we've written it as a x to a power, we can simply apply our power rule. We're going to bring the power down, so I'm going to bring the 1/3 power down, and then this is going to be x to the 1/3 minus 1 power. Well, 1/3 minus 1, get common denominators and all that good stuff, would give you x to the negative 2/3. For our final answer, we want it to be in simplest form, and we kind of recall that from algebra, if something has a negative exponent, it's not considered to be simplified. So I'm going to bring that x to the 2/3 into the denominator, do the reciprocal, and that will change the sign of the exponent. So there we have it. The derivative of the cube root of x is equal to 1 divided by 3x to the 2/3 power. If you wanted to, it's perfectly acceptable as well if you feel like going back to a combination of roots and powers. X to the 2/3 power would be the same thing as the cube root of x squared. So you could have also written the radical form as well. Let's take a look at part C. We want the derivative of 1 divided by x squared. Again, let's take the key step of rewriting it first. We want it to look like x to a power. This would be the same thing as x to the negative second power. I can apply our derivative rule. We're going to bring the power down, and then we're going to reduce that power by 1. Negative 2 minus 1 is negative 3. So this is going to be negative 2 over x to the 3rd power. So in part C, the derivative of y prime is negative 2 over x cubed. Question 3 asks us to find the slope of the graph of f of x equals x to the 4th at each value of x. We recall that we remember that slope is synonymous with the derivative. So we need the derivative of x to the 4th. That's going to be 4x cubed using the power rule. Bring the power down. So it's going to be 4 out in front multiplying to x to the power reduced by 1. 4 minus 1 would give us 3. From there, we can find the slopes at each of these points. When x equals to negative 1, the slope would be given by the value for f prime of negative 1, which is 4 times negative 1 cubed, and that should be negative 4. When x equals to 0, the slope is going to be f prime of 0, which is 4 times 0 cubed, which is 0. And then when x is equal to 2, the slope is going to be f prime of 2, which is 4 times 2 cubed, which would be 4 times 8, and that will be 32. So once again, if you hear the buzzword, if they say what is the slope of the tangent line, or if they say what is the slope of the curve, that's simply going to be the derivative evaluated at the point. And for us right now, we're finding derivatives by using our brand new power rule. Theorem 3.4 is the constant multiple rule. And what the constant multiple rule says is, let's suppose you have a constant c times some function of x. Then to take the derivative of this expression, you can simply kind of pull the constant to the outside. So you can pull a constant outside of a derivative, and then it's going to simply be the constant times the derivative of f prime of x. Let me go through an example 5 part A. Let's use this constant multiple rule, and I'm going to kind of show it in great detail, but then we'll just kind of use it a little more loosely from there. So if I wanted to find the derivative of 5x cubed, this is going to be d dx of 5 times x to the 3rd power. Constant multiple rule says I can take that constant 5, move it to the outside. It's going to be 5 times the derivative of x cubed. We know from a little bit ago that the derivative of x cubed, using our power rule, is 3x squared. Bring the power down, reduce the power by 1, and now we can multiply that derivative by the constant 5. So we get as our answer 15x squared, and I'm only showing all of this writing so you can see exactly how this works. In practice, if I was working this out and when we do the next batch, we'll simply just leave the 5 there, put a multiplication symbol because it's a constant multiple, and then we'll just put the derivative of 3x squared directly behind it. Derivative of x cubed, that's the 3x squared, and so immediately we would get the 15x squared. Let's take a look at another one. In part B, we have 2 divided by x. We want to first begin by rewriting this. So rewrite it as 2 times x to the negative 1st power. we can now go ahead and apply our product rule, our constant multiple rule. We're going to leave the constant of 2 alone. And now we're going to multiply that by the derivative of x to the negative first power. The exponent comes down. We reduce the power by 1. Negative 1 minus 1 is negative 2. So we get 2 times negative x squared, which is negative 2x to the negative second. And then we don't want to leave it with a negative exponent. So the exponent gets moved into the denominator, and it now becomes negative 2 divided by x squared. Be very careful with your algebra on this. I see a lot of students will sometimes make a mistake in terms of the sign of the coefficient versus the sign of the exponent. We can't leave things with negative exponents, but a negative coefficient just simply means that the quantity has a negative value out in front. That will not change whether you do a reciprocal or not. Let's take a look at part C. Again, if I want to, it's a very minor rewrite, but I find it oftentimes to be very helpful. If we have 4t squared divided by 5, that's equivalent to the fraction 4/5 times t squared, and now it looks more directly like a constant times a function of t. We can apply our derivative. F prime of t would be equal to, let's leave the 4/5 alone. We're going to multiply it by the derivative of t squared. The derivative of t squared is 2t. And then if I want to, we can combine the constants. 4/5 times 2 would be the same thing as 4/5 times 2 over 1. And that would be 8/5 times t. So f prime of t is equal to 8/5 t. Let's take a look at part D. Again, we want to do a rewrite on this to start. We can think of this as 2x to the 1/2 power. Let's take a derivative. Leave the constant multiple 2 alone. It's going to be 2 times. We bring the power down. X to the reduce the power by 1. It's going to be to the 1/2 minus first power. 2 times a half is 1. And then 1/2 minus 1 is negative 1/2. We can go ahead and rewrite it. This would be 1 divided by x to the 1/2. So y prime is 1 over x to the 1/2 power, or you could even call it 1 divided by the square root of x, if you want to go back to radical notation. Let's take a look at the next one. Again, rewriting is going to be a huge part of this. Ultimately, we want to rewrite it so that we end up with a constant times x to a power. Here, the first thing we can do is we can kind of split it apart. Actually, let's do it like this. Let's first revert back to fractional exponents. The cube root of x squared would be the same thing as x to the 2/3 power. Presently, our x is in a denominator. We don't want x to be in a denominator. We want to have some power of x. So we can move that out of the denominator by making it a negative 2/3 power. So our original starting function is equivalent to 1/2 x to the negative 2/3. And now what we can do from here is we can actually go ahead and apply our derivative rule. Y prime is equal to, leave the constant of a half alone, times, we're going to bring the negative 2/3 power down, and now we need to take that negative 2/3 power and subtract 1 from it. 1/2 times negative 2/3, that's going to be negative 1/3, and then negative 2/3 minus 1 would be negative 5/3. So y prime is equal to, we have a negative 1 over 3, and we're going to bring that 5/3 x to the 5/3 power into the denominator in order to make the exponent positive. So there we have it. Y prime equals negative 1 divided by 3x to the 5/3 power. For f, we have y equals, we can rewrite it as negative 3/2 times x. We have the constant multiple negative 3/2, and then the derivative of x is simply equal to 1. So we get the derivative negative 3/2.